Welcome back, everyone. So this is the second webinar on our Brain Python Alpha series. This webinar will be focusing on advanced research workflow, and also we'll talk a little bit about research. In the previous webinar, which is webinar one, we cover the foundations, how to set up the brain session, how to use brain cache, how to fetch data, define the alpha with the alpha decorator, how to run simulations, how to design and implement your operators, and do like a very, very basic parameter swap within BrainLab environment. If you haven't watched that session, I will highly recommend you to do so. The recording is now available on the community. That should help you build like an important foundation of how to create alpha, create Python, brain Python alphas. Additionally, we also introduced the Python Alpha competition in the last webinar. And as of today, I think the competition has started. So you may find more details and guidelines available in the competition page already. So for today's session, what we want to do is we want to go deeper. The agenda for today is first, we'll revisit BrainLab simulation as your very fast debug and research iteration tool. And I'll share like specific tips for speeding it up and debugging it in a more systematic way. Then we'll talk about how to maintain a clean operator workspace as your library and arsenal grows. After that, we'll go into like very deep into the store backed operators. This is a very important optimization pattern for your Python alphas that requires large loopbacks. We'll also cover a bit about data cleaning, which is often where the best research insights come from. We'll also discuss how you will want to implement risk-neutral performance on Python Alpha. Then we'll look at how to structure a full research notebook within BrainLab environment. Finally, we'll do a more structured research. We'll look at the result and see how to like persist them for later usage. So let's get into today's topic. So we'll start with the first section, which is the BrainLab simulation for fast iteration. Um, so a very quick recap, as we mentioned last time, there are multiple simulation paths that are supported by BrainPython Alpha. Um, but mainly it can be divided into two parts. One part is if you run the BrainLab simulation, which the syntax will look like you call the generate alpha metrics, you call the generate alpha positions, and then you call the generate alpha stats. Everything runs on your BrainLab machine, and everything runs with the cache data. On the other hand, there's the actual simulation. Um, this is the accurate remote path. You will need to call brain simulate if you're in BrainLab, or you can just send the simulations through the platform UI, which you can just select Python as a language from the drop-down menu. At either of this approach, the backend runs the actual full simulation pipeline. This webinar will be focused more on the BrainLab simulations, but I think the recommendation on how you want to build, test, and design your operator space that will also be applied to actual simulations. Your For BrainLab, you'll use it for like I would say most of your development should be happening on BrainLab or most of your research iteration. I would recommend you to validate your best alpha with the actual simulation before submitting it as the final Python alpha. So there are several speed up tips. Let's start with three concrete one to make BrainLab simulation as fast as possible. The first one is you can actually choose to cache the data up front. So you create a brain cache once at the start of your notebook session and pass it to every simulation code. Without caching, like the simulation engine will try to re-download data fields on every code. Um, Usually, what I imagine people doing research is that they will decide to work on a specific data set, maybe several specific fields, and then they try to like find alpha within that field. So I think like caching those several datas upfront will make the following simulation a lot more easier. The second thing is to disable visualization. So um, there's a there's a usage here. Yeah, when you're passing the simulation setting, remember to set for the visualization to false. So this when you're running like multiple brain lab simulation, this setting it will generate the P&L chart each time, which creates overheads and will clutter your notebook output as well. The third thing is to start with a smaller look back. Um, During the you, is I think especially during the initial development, use something like loopbacks equals to 5. If the alpha logic correctness doesn't depend on having a large window, of course. Um, Using a very small loopback, you're essentially checking for errors and NAND handling. You're not really tuning performance to say. Once the logic is correct for your Python code, it's now safer to scale up to actual targeted something like maybe 252 lookback days. But before you ensure that everything is correct, I will highly recommend you to start with a smaller loopback days, or even start with a dummy data in the first place. So here's what the fast iteration loop looks like. You import all the necessary modules that you want. You define you need the brain session. Remember that you should always set raw equals true if you want to run the brain lab simulation, because this way you'll get the actual unadjusted data and also the data with the actual data type. This is important. Second, you want to initialize your cache. Then if you define your alpha like this, then you define the settings. Remember to set a smaller loopback. Remember to set visualization to false, and then you can start the alpha matrix. You can start with the generate alpha matrix, run the generate alpha positions, and finally run the generate alpha stats. You can time each call. You will know like how long your simulation takes. Yeah. Okay. Um, so like if you do this correctly, usually I would say a small look back simulation on like something like USA top 30,000, it shouldn't take longer than I would say a couple seconds, maybe up to 10 seconds. Of course, it depends on your operator design, which we'll dig deeper into later. Um, Now I would recommend this development workflow step by step. So in the first step, in step one, I would recommend you to write your alpha with a small loopback, as mentioned before. In step two, run generate alpha metrics. If there's any error, try to fix the alpha before going any further. Step three is to inspect the alpha metrics. Check whether the value looks reasonable and is there like any NaN value inside it, and is this NaN value expected. Next, you'll want to run the full pipeline and check the performance, something like the sharp, returns, and turnover. Adjust the operators and adjust the parameters you want to use and rerun it. Because the cache is warm and each iterations of different simulations using the same cache will be very fast. Once the logic is stable, you can scale up your loopback days to longer days, and whether you think is more appropriate or whether it's required in your alpha logic. Finally, you can validate your best alpha with the actual simulation endpoint. The brain does simulate your alpha function comma settings. This way, you can have an official alpha ID, and then you can submit that afterwards. Whenever your alpha doesn't like behave as expected, I will suggest you to work through the following checklist. The first thing is oftentimes if you're not aware if you use the brain lab simulation, we'll try to mimic the actual simulation endpoint as much as possible. So whenever you have an error in the actual simulation endpoint, you will not get a very concrete error message for like most of the time. But if you use the brain lab simulation, usually it will generate that error message for you. So below is some very common error message that will tell you like what's the issue. Um, so for example, if it returns something like alpha factor is none, then it means that your function return none instead of a numpy array of float 32. If your alpha factor is not an ND array, so obviously that should be an ND array. Oftentimes you may accidentally return something like pandas series set, for example, or whether your alpha matches the universe size. Because as mentioned before, your returned ND array should always have the same size as the number of instruments within the universe. If your number, like if your output has a wrong number of elements, then that will never pass this function. Also, if you're using the store functionality, there's a possibility that you store an unsupported type, or you when you're storing, like if you ask for float on the array store, but you store an integer into it, that will also raise an error at this point. Yeah. The next step for your debugging checklist will be to inspect the alpha metrics. Um, so I think this one will like be rather kind of like unfamiliar if you previously worked mostly on fast expression alpha. So there are several things that we want to check for whenever we want to examine the alpha positions generated by the like the generated alpha positions function call. The first one is you want to check whether there's all NaN rules, meaning that for any given trading days, there's no valid instruments within that day. Essentially meaning that you're not allocating any positions on like like trading days, which should be unnatural because supposedly your alpha should be generating consistent signals throughout the history. So first thing is to check for if this kind of date exists. The second thing you want to check for is there any infinite value that is showing up in your computations? So unlike fast expression operators, you have to handle something like divide zero or divide value that is very, very close to zero, which will often lead to very large value, sometimes lead to infinity value. So this is also important. If you have have this value in your alpha matrix, it will often cause issue in something like neutralization, or cause some issue with the scale to book size, or basically every operators after the infinitive value shows up. I also highly recommend you to check the value range. So of course, checking the min max, I will personally also check something like the 95 percentile, the 5 percentile of the alpha position matrix, so that you know that whenever you're computing along your alpha logic, that your value distribution, the tail of it still falls in a reasonable value, that it will not, whenever like you're doing neutralize, you will not squeeze everything to very left or very right, causing you to essentially only longing one stock and shorting the rest of the universe. Also, I recommend you to check whether the alpha is market neutral. Um, so if you just compute the average across the axis of one, it will give you the average value of each day's position. It should be close to zero. I recommend you to do that within your own alpha function, but you can also rely on the settings itself. But I think explicitly handling that in your alpha function should be a better research practice. The final thing is you will also want to check how much value is changing from day to day for your alphas. This is also sort of a sanity check because if the value is zero, it means that your alpha is constant. You're not actually using the real data, you're not actually updating as the data is also updating. So that's also a very early warning sign as well. Um, the next step will be to check the positions after generate alpha positions. Um, yeah, so I think similar concept can be applied here. You want to check the value, the range of the position. You also want to check the long count and short count. You can also plot the distribution of your position, plot a histogram for yourself. That way you know whether the distribution is too skewed, whether its kurtosis is too high or too low. Yeah. Also, you can also check whether your alpha is long-short balance after applying all the settings you specify for that alpha. Once you check everything is within your expectations, next step is you can start to profile for bottlenecks if you notice the runtime is on the slower side. Um, in this example, we're timing each function call within these three steps of generating the final stats for brain lab simulation. But I will say like most of the time, the first function call, which is the generate alpha matrix, it will be the dominant factor. It should take most of the time of the computations. So what I will actually recommend you to for you is you should time the operator call or the function call within your alpha function. You can either ask it to write the time to somewhere on the disk, or you can just print it to the print it out. I think that also works as well. Um, yeah, so once you notice that if certain functions are the bottleneck, then you should start considering using sortback operators, which we'll cover next. Okay, so in the previous in this section, what we're trying to do is depicting a workflow of what you should start and and the steps that you should follow, and also the common tips and error that you may face during simulations. Yeah, so let's move on to the next section, which is maintaining your operator workspace. Um, as you research progress, likely you're going to accumulate a library of operators, hopefully. Keeping that library of operators organized, I would say, is very important for your research journey. It makes your future Python alpha faster to write, easier to like review, and simpler to debug. The best practice is to keep all your operators in a dedicated notebook cell will work at the top, or personally, I prefer to keep it at a separate .py file that you can import for your BenLab simulation. Don't scatter your operator definitions throughout your notebook. That way, you're having a huge trouble trying to identify which operators that you actually code before calling the alpha function. Um, this is a well like organized operator cell that should look like something like this. You have each of your operators laid out and with a very simple one-line comment describing what it does and the input and output shape of that. And whether will there be any sort of NaN behavior, like how does it deal with NaN? Does it also generate NaN, or does it replace it with any like zero or any consonant otherwise? Yeah. This will help you come back to your notebook like weeks later, and it's still easy for you to pick up. Um, if your operator library grows large, honestly suggest you to put that inside a standalone Python file and import it when running BrainLab simulation. Of course, when you want to submit an alpha, then you will need to like extract those definitions out of the PY file and pass it into a standalone, either a PY file or a standalone cell. In this case, I'll suggest you use a PY file, and there's Python modules that can help you to extract function definition and then write that function definition again to another PY file. But I think that's something that you can explore on your own. The next one is approaches, which I think is very valuable, is to understand how important store back operators can help you with speeding up your simulations. Um, so in webinar one, in the previous webinar, we introduced the store as a way to persist state across time steps, basically across different days. And we showed a very efficient incremental mean as an example in that time. In this section, we generalized this pattern into a full system for like building your own store back operators. So um, to understand why we want to do this, the first thing is we want to know why operators can be slow. Basically, at the backend, the simulation engine will call your alpha once per different trading days, and based on the look back windows you specify, we'll be passing a sliding window of data into your callback function. Um, Most of the window is unchanged from the previous step. Even all of the window will be unchanged except for the latest state that is entering the window and the oldest state that is exiting the window. If you write a stateless operators and apply onto this window, it will recompute everything from the top to the bottom. But what you need to do is actually just remove the top and add the bottom part, which is the latest information. Um, Here's a very simple example. Even if you're running something like rank and you apply like have a look back days of 252 days, and that way what you're computing is you're basically applying rank to 3,000 instruments roughly on 252 iterations. Even though out of the 252 iterations, 251 of them are actually ranked yesterday. And when you apply the TS mean data returns 252, it will sums the 252 rows every step, even though 251 of those sums were already computed yesterday. This waste around like 253 more times of unnecessary work, which you can save from if you utilize store efficiently. So the important idea here is always, of course, you should start with stateless first. Before I show the store back approach, let me be clear with the workflow. So don't start with the store back operators. Always follow this order. You should build a stateless operator first. You should get the logic right without worrying about how you want to handle the incremental state. And second step is you should validate that it is working. So what you should do is you should run brain lab simulation. You should create test data. You should create some dummy value and confirm that indeed the status operator is working as expected. Then what you want to do is you want to profile. If at the small lookback days the cost is negligible, try to increase the loopback days, try to increase the size of your ND array that you're passing in. You can choose whether you want to optimize it to a store back operators if the speed is really the bottleneck. So the next step will be to transfer that into a store back. But I would say that's only like you want to do this only after validation that this step is actually needed. Store back operators are harder to debug. If your alpha has a bug and you want to find it in the simplest stateless version, not buried into some like incremental sort of stuff and with a bunch of bookkeeping around it. Yeah, so the core idea is start with stateless first, even though it is slower in most of the cases. Validate that it is indeed working. There's no bug, like either big bit when the operator starts or when the operator ends. Make sure that the output is also what you desire. If you write something like a neutralized operator, validate that actually the summation of the output will be 0. Something like this will help. And then you can start profiling it with different size of input, understand whether, or you can just review the code actually, but you should be aware that if the speed is the bottleneck of your alpha simulations, then you can try to transform this particular operators into a store back pattern. Okay, so I think that's hopefully help you understand under what kind of circumstances I would recommend you to start working on a store back version. Let's say if you want to use that in your alpha, um, you have to declare all the store variable names upfront in the alpha decorator. A single incremental TS-min will need four operators. Oh, sorry, will need four variables. So you need the summation, previous summation, you need the count, you need the oldest, you also need n for tracking like how many of them. Um, so if your alpha use three incremental operators, there will be like something like 12 store variables to name manually. And if you call TS-min twice, once on your returns and maybe once on your column data, each cell will need like its own four variables with different names. Otherwise, you'll be using the wrong store variable for the wrong function that actually uses it. So the solution would be, I would suggest you to write a sort of a utility class or a utility function called operator context to solve this. Essentially, it is working like a registry. So you tell it which incremental operators you plan to use, each with a unique label, and it can generate the complete store variable list for you automatically. Um, yeah, so I think something like this will help you quickly generate the variable names that you need, and then you can pass that into the decorator itself. So this, I think this is a very brief example of how it may look like. So for example, you initiate a context manager, then you register something like rank, and it is a cross-sectional operators, and then you register something like return min, which is a TS-min operator, and volume min, which is a TS-min operators. What it will output is the syntax that you will need for the store for the alpha decorator store variable. So each label will produce prefix store variable names. Yeah, and the prefix will ensure that there will be no collisions, even if you register multiple operators of the same type, as long as you give it a unique name. Um, there's one important caveat that you cannot write alpha store like you cannot write something like this stating the alpha decorator and store equals context dot store varies. This is because the alpha decorator argument are parsed directly from the source code, and it only taking literal list, not variable references. So this workaround is to print the context store variables and copy the output and paste it directly into the decorator. Um, yeah. There's also an sort of an alternative workaround. Um, you can set the alpha store to the context store variable after the function is defined. But I think this will only work if you're working with the brain lab simulation. If you want to work in the actual like in the actual simulation code, this may not work. Yeah. Yeah. And below is the full operator context implementation. Um, I think it's quite straightforward. So you basically init that and you keep labels within memory. And then you have a very simple register function, which will read every like every member function you have and understand what kind of stuff it need. So whenever you create your own operators, remember to register it as a member function within this class. This way you can easily generate the store variable whenever you needed it. Um, yeah. So the operator context only runs at the runtime. That you only need to connect to runtime. is only used at the setup time to generate the store variable list. At the runtime, the incremental operator functions will access the store directly, and you will check for the registry that it was told to use. So for example, the setup time, I'll use the OP context and register a name to RET5. And then at the runtime, my operator argument will have something like TS being that underscore inc, meaning that it's an incremental TS min, and it will take into data that returns as input. 5 is the loopback days. You will also consume the store, which is the dictionary, and then you will also consume the registry for this particular operator code. So it will know that it should get something like underscore op underscore ret5 underscore sum, which previously it has been registered here. So this is the sort of the way that you will want to use this. Yeah. So even for cross-sectional operators, something like rank, um, the key idea for this kind of operators is to cache the full output matrix. So on each step, only shift the cache up by one row and compute only the newest row, rather than re-ranking the entire window. I think this is often overlooked. So actually, no matter which kind of operators you're using, as long as you still want to consume data other than the latest day of data, oftentimes this kind of operators may be considered for store back design, especially that if it's like causing a lot of consuming a lot of resource. Okay. I think for incremental time series operators, it's more obvious. So for something like time series min, you want to maintain a running sum and the failure count. So at each step, what you will do is you will add the latest row and subtract the oldest one. And divide it by the number of count, then you will arrive at the time series average of that instrument at that given day. So you only do 3 operations instead of adding the number of days you needed, the loopback days you needed, over over and over again. So this way you can achieve a very high speed. So putting it together is that you will want to first start with the stateless version. It is more simpler to implement, and it's also easier for you to debug yourself. Once you finish the stateless version, and you find that you need the speed up that can be granted by improving into a storeback version, then you can start to implement the storeback version. Um, I recommend you to write the operator context, sort of a helper class for yourself. Of course, you can find other ways for you to systematically register this kind of stuff, but I think this is a more cleaner approach, in my opinion. Yeah. So in this example code, I'm using the empty list as a placeholder, but I will swap it to the actual context store variables after I define the alpha function. Yeah. If you actually run this, if you implement this and run this, um, you'll notice that these two different alphas, they actually produce the same result, but fast alpha is very, very fast. I think I run the test on, I think around, if you're running at like 200 days, the speed up would be like 100 more times than the stateless version. And the speed up will be even higher if you have multiple stack of operators within your alpha code, which will likely be the case. This speed up will be even higher because you're avoiding a lot of redundant computation that are already computed yesterday. But remember that before trusting the store back version, you should always validate it against the stateless baseline. So something like running both of them through the same sliding windows or the same dummy variables to compare its output. I think it's also always a good idea. And I think below is a very simple example of in under what kind of circumstances will store back operators help. So for example, like rank is actually quite expensive. Rank will be very helpful if you actually store all the intermediary rank value that are already computed in previous days. So same applies to Wingsurise, group rank. For time series operators, I think it's very obvious. But for something like neutralize and scale, these two, I think it's marginal. The improvement will be marginal. For some like arithmetic operators like addition, subtraction, log, exponential, those kind of operators, I don't think you actually need to use the store operators. The store pattern. You can just recompute it on the whole matrix. The performance improvement from going from the the stateless version to the store version, the performance improvement will not be that substantial compared to the operators over here. Yeah. So I think the rule of thumb here is that if the per row computation involves something like sorting or percentile, caching will pay itself. But if it's just very simple math, then the memory copy that actually causing from the using the store overhead may dominate the actual computation. Okay. So that's the section on how you should work with the store variable more deeply. So to sum up, I would suggest you to first start with the stateless version, which is not using the store at all. Once you validate that the stateless version is indeed working, and you notice that the simulation speed is of bottlenecks, then you can start to write the store version of the operators you use within your alpha. You should validate the output should be consistent with the stateless version. You should also be aware that you should also handle for edge cases. Something like what happens at the start of the simulation when the simulation days are less than the loopback days you're asking for. How does you handle with that, and how does your store handles with the first initiation of the very first day? So this kind of stuff you need to think about, and I'll also recommend you to write something like operator context for your own self, so that you can organize the operators more nicely, more clean, and it's also easier for you to reuse the function you defined in the past and be able to pick up and integrate that into your future alphas. Yeah, so I think that's the overall recommendation I would give to operator design as well as how to utilize the store function. Um, the next part will be focus data cleaning. I think this is one of the most underrated alpha research tips. It is to take one data field and clean it very thoroughly, rather than combining many fields like superficially. The best alpha often come from a very deep understanding of a single data set or sometimes a very single data field. This is an sort of an end-to-end sort of a workflow using the implied volatility field as a very simple example. So the first, we have talked about this in the previous webinar. You can fetch the data from the brain session, and you should also fetch the universe diagram as well. Next step is you want to check the number of name value and the number of zero value throughout this data. Of course, you should also check the type of the data to understand which kind of NAND that you're dealing with. If you remember in the last session, we showcased an example where if the data is of type integer, then the NAND value for integer will actually be the minimum value available for NumPy integer, which I think is something like negative 27 billion, so something like that. Yeah, so the type of the data you should be wary of, but this particular field is of float. I think it's float 32. So it's safe to directly check for NAND value. Next step, you want to write something like a very simple forward field and understand whether the forward field help with filling in NAND value of the data. Next step is you can easily check for distribution for outliers. So as I mentioned before, I think a very good rule is to check the minimum maximum, also the 99th percentile and the very first percentile. Next is you can start build your alpha from the clean data. Here there are several patterns. Like I think is more useful. So the first thing is you should use the data and cast it to a known type. In this case, I recommend you to work with NumPy Flow 32 or NumPy Flow 64. Next, you'll want to forward fill the data according to the shape of the given data. Because whenever you're calling the data, even if you specify a loopback dates to something like 20, at the very start of your simulation, the actual date will not be 20, it will be something like maybe 1, 2, 3, 4, and it will started to extend. So I think it's better for you to actually call the actual shape of the data that you're actually seeing. Next, I think is simple. It's just computing the average and standard deviation, and be aware of whether it's NaN or not. So if it's NaN, it will be just ignoring it, and then make sure that you're only computing the value where the standard deviation is larger than 0. And then what we want to do is want to compute the z-score value of that. So we'll be subtracting the average and dividing the standard deviation. So when doing this computation, you should always be aware that you're not dividing 0. So it's a good pattern that you should check this over here. Yeah, so I think this is a pretty quick section. So you should start with, obviously you should start with looking at your data, checking the value, understanding what kind of backfill that you may want to apply to a given data. Depending on the data idea, depending on the data signature, you may want to do something like forward fill, or fill it with a certain constant or fill it with a group value. And then when you're doing the actual computations, you have to understand what kind of insight have you learned from the from the data digging part. For example, if you notice that the data will have a lot of 0, then you may be aware that you should not divide the data directly. You should always check whether data is close to 0 and then run the divide on values that are far away from 0, or remember to add a constant to the data. Yeah, so this also applies to when you're computing the z-score of the data, when you're subtracting average and dividing standard deviation. As a personal tip, I also recommend you to try out different variations of z-score. For example, you can subtract by median and divide it by standard deviation, but replace everything that requires computing mean average to median. That way you won't be skewed away by extreme outliers, and you'll be able to maintain a more centered and a more, I would say, more clean distribution of the final product. Yeah. So this is a very simple example how you could see on on a particular data field. Next is we'd like to talk about the risk neutral performance. So this is exactly the same as you will want to do in your own fast expression alpha. On Brain, we directly offer it within the neutralization settings. So you may be remembering something like slow, and fast, statistical, momentum and reversion, something like this. Usually these are risk factors, something like market beta or industry or some common alpha signals, for example. And what we want to do is we want to remove these factor loadings from your alpha positions. Unfortunately, this is not support. You cannot specify something like neutralization equals slows within the BrainLab simulation. You can use it in the actual Python alpha backend simulation, but it is not available within the BrainLab fast simulation that you want to use for your debugging and research purpose. So there are several alternatives that you may try to proxy it or try to integrate that into your own alpha research pipeline. The first one is, of course, you can define your own set of sort of an factor loading that you want to remove, and you can do that by implementing your own group neutralize, your own factor node, or more correctly, I think you should implement your own multi-regression that runs your alpha position to a wide range of factors and get the residual of the results and then scale it back to an alpha positions. That way, you can somehow proxy what will be the performance looks like, given that if you control to a list of well-known factors that you are aware of. When you're submitting the alpha, you can submit the control version, or you can actually submit the uncontrolled version and use the brain risk neutral simulation settings. The next, the other way, the other approach is instead of directly removing the factor exposure from the alpha position itself directly, you can define something like specific returns, which are their returns that doesn't contain the factor exposure. So what I'm saying is that your alpha, like when we're removing factor exposure from alpha position, our assumption is that your alpha position actually contains not just alpha, but other factor loading as well. And what we do is we remove the factor loadings from your alpha position, and then times it to the actual return matrix. But you can actually do the other way around. You can sort of compute the return matrix and remove the factor return from the return matrix and multiply the factorless return matrix to your raw alpha position matrix. This is somehow similar to the risk neutral PNL you saw on the platform. Yeah, so this is also another approach that you can do. And you can actually like expand on this idea when you're running simulations, when you're running like lab simulation to get a very quick iteration and maybe to fit towards certain stuff. Um, like tomorrow's return isn't the only target that you can look at. For example, you can do something like instead of creating the alpha with the highest sharp, you can first try to predict next day's return. And based on next day's returns, you can try to build an alpha matrix based on your prediction. So what I'm trying to say here is that don't let the return, like the raw return evaluation concept, limit your creativity. There's multiple ways that you can do that will, at the end of the day, will generate an alpha metrics that you're used to, but there are different ways and different approach to let end go. So be very creative about this. I think using something like specific returns is only one method. You can also do something as crazy as you can define a return and then neutralize that return with all the alpha you submit previously, so that the new alpha must have returns in the leftover of your previous alphas. Yeah, so there's a lot of flexibility here, not just about creating risk neutral alphas. But I think as a reminder, for the actual risk neutralization, for the accurate result, you always have to use the simulation endpoint using the brain.simulate and specify the neutralization to something like slow. That way you'll be able to actually call the actual risk model and then neutralize to that risk model. Yeah, so I think that covers the fifth section. Now I think we're approaching the final stretch. Yeah, so this is the so I think it's sort of the final part of today's webinar. So I think at this point you should be rather comfortable and familiar with how Python alpha research should work. And as your research becomes more systematic, the structure of your notebook start to really matters. A well-structured notebook is easier to revisit, to understand in futures, and it's more easier to extend as well. Um, Here will be the four section that I will recommend. The first section will be obviously the imports and all the brain cache and simulation settings. Um, should be over here. And then the next sessions should be the alpha definition. So you can also put your operator library. I would suggest honestly put that into a standalone Python file. And you can think about if there's any other method that you can copy the definition from a Python file and then write it directly into another alpha file. But yeah, so you should always keep that at the top or in a separate Python file. The next section should be your actual alpha definition. And remember that there should be one alpha definition per cell. Yeah. And the next session is based on the alpha definition, you can run the parameter sweep function that tries to optimize for different parameter values. Um, there are multiple ways that you can design this kind of sweep. There's the very brute force version. There's also a more delicate version that we'll be sharing in the next webinar. So you can look forward to that. Finally, the final section of your notebook should be analysis. So if you run like multiple simulations or you generate the alpha position matrix, you want to understand what is its correlation to the next day's return. You can run something like this in this part of your notebook. If you run any sort of iterative optimization, you could do something like training and validation split. You can do something like filtering to filter out good part of the iterations. You can also do something like portfolio analysis that you understand as a batch how you're doing with this amount of alphas. Yeah, so about the research part, this is a very simple example that you can generate something like, so in the previous session, we use different loopback values. But as you may already notice that there are multiple parameters that you can use within your alpha, and of course within the operators that within the operators that you self-define. So one way you can do is you can create a parameter grid, and then you can generate all the combinations available, and make sure that your operators are supporting the parameters that you're using, and then you can load that parameters out, and then redefine the alpha function, and then generate the alpha matrix, compute the actual stats. You can compute all the other stats and record it and add that into the results. And then finally, you can print that results out to understand under what kind of combination that this is working. But you may be already aware that as the number of parameter options grows, the number of combinations will grow exponentially. So you should think about how you want to be parsimonious about the number of parameter space that you want to define, and also think about, is there a better approach other than like brute force to run all the simulations? Even if brain-less simulation is fast, you shouldn't be wasting compute on this kind of stuff. Yeah. Um, I think that's almost at the very end. There are several stuff. So for the result analysis from the parameter sweep or the grid search, of course you can do something like you can ensure a basic performance similar to what you will see in the submission test in the actual Python alpha. So you can require it to at least to have certain amount of sharp, you at least to have to be within a reasonable tone over range. You at least to have fitness larger than one, so on and so forth. Besides the standalone, like the standard alpha submission test, you can always resort to portfolio analysis. So this is what you will not be available to do if you want to work with something like fast expression alpha. With fast expression alpha, what you could do is you could average the PNL directly, but that is not very accurate and is not incorrect. It is incorrect. It is not correct. Because if two alphas have different positions on the same stock, let's say if it's opposite, then the exposures will cancel out each other at the final portfolio level. But their individual P&L does not reflect this kind of this kind of advantage. So the right approach is always to actually average the position metrics before recomputing the P&L for the combined position. So what can this be used for? This can be used for like evaluating whether your iterations is having progress, evaluating whether this data set is informative, evaluating whether certain operators or certain approach are adding value to your previous trials. I will say this is a more statistical significant way of proving that what you're doing is actually mattering. Yeah. This is the part where you visualize the P&L from your portfolio. I think it's quite straightforward. Oh, there's also another important thing is that if you're running any sort of research or multiple simulations within your notebook session, it is important that you periodically dump the result to disk because there's also a timeout setting on your brain lab session. So if you dump your result periodically, personally, I would suggest something like every 20 minutes or every like 1,000 simulations or every 500 simulations. That way you will be able to understand what you have ran before the previous session closed, and you'll be able to pick up from there, or you'll be able to analyze the results when you're able to rework on the previous stuff that you have ran maybe several weeks ago. And as I would say, the common way is to dump it into a pickle file. Of course, you can work with something like a JSON or other format. I think it depends on you, but because likely you'll be working with a bunch of function definitions, dumping into a binary format, a pickle file will usually be the best approach. If you dump it to a pickle file, you can easily load that out and you'll be able to review the results and also see the actual function code again. Okay, so I think it's the final minutes of today. So today we talk a lot about a wide range of topics, but mostly we focus on how you can utilize BrainLab as one of the very important tool when you're creating Python alphas. There are several concepts that you can borrow from implementing your own Python operators outside of BrainLab. If you prefer to work directly on UI, I think that's also doable. Several concepts. The brain simulations, it should follow the generate alpha matrix, generate alpha position, and generate alpha stats. The actual simulation is always the ground truth. It is production accurate, and it will need to be used as final validation. In order to have a fast iterations, you should cache your data up front, you should set visualization to false, and you should try with a very small loopback first. For debugging alpha, remember to check the alpha metrics for NaN values on a time series basis and also on a cross-sectional basis. You should always check the value range, check whether your alpha is long-short balanced.